Should probably not be on mute. All right. So we have got parametrics. So real quick, you have dealt with parametrics at least for a very, 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 very short period of time when you were inside pre-cal. Unless, of course, you took the summer pre-cal class and you have no clue what the heck we're talking about with this parametric stuff. Good times. You guys did touch on parametrics a little bit, right? Okay. Probably. But what I remember from pre-calculus is a totally different thing. That's okay. That is all right. So, real quick review on what parametrics are. Essentially, it's going to be taking a function, and it doesn't necessarily have to be a function that we can do as like a y equals x function. But essentially what it is it's realizing that we can connect an x and a y variable through a third variable, where x and y aren't necessarily related to each other, but as that t passes along, as long as x is some sort of x with respect to t is continuous and y with respect to t is continuous, then our parametric function, which is kind of like a piecewise function, except that the x and y go together. But the concept of these two functions being married together through this t variable would create a smooth curve. For instance, if I take the graph y is equal to negative x squared over 72 plus x, which, by the way, is a situation where we are shooting some sort of projectile at a 45-degree angle with an initial velocity of 48 feet per second. Why did we choose that one? Because that's what the book chose. Excellent. Then this is the equation that winds up coming out. Well, one of the things that's useful, you recall in physics, one of the things they would ask you is something like, when does the projectile hit the ground? And you had to figure out, as the function went up and down, you had to look at the y variable separate from the x variable. When you did that, you looked at a parametric function, parametric equations. All right? We go through, there are some words that are defined here. We call one a plane curve. The reason why we're going to call it a plane curve and not necessarily a function is because you can get some wacky parametrics that, and you could actually graph something like that. Yeah, that is possible. So I'll see if I can come up with a good example of that later. And and so that's what we're looking at through all of that. So, example one, how on earth do you sketch one of these curves? Remember that we're looking at x and t as two separate functions with respect to t. So what I need to do is I need to see what is all the x values at specific t's and what are all of the y values at those specific t's. So what we do is we come up with a table of t values and evaluate the x's and y's that happen at each one of those t values, and each one of these combinations is its own point. So you can see we have the point 0, negative 1, negative 3, negative 1/2, negative 4, 0, negative 3, 1/2. And we can see that we've got these different points. So all we do is we come up with this table and create these points. But you'll notice that there's even more than that on this. You'll notice that there are arrows. The concept to this is that t variable is always increasing from my starting value to my finished value, which means not only is this the graph of the function, but this graph also has a path that it must travel through. We don't go backwards along the path as much as we have to increase along the path, so there's only one way to flow along this particular graph. All right? So that's going to be how we're going to graph it. It's not too bad. We'll do an example of it. The other thing we'll need to be able to do is something called eliminating the parameter. Sometimes I just want to know what is y equals x or x equals some function of y. What's the relationship between those variables without the t? Just like a system of equations, essentially all you do is solve for t somewhere and substitute it in. You will get, you could get some function of y as x. You sometimes will get y as x as a function of y. You'll notice that this parametric equation is kind of weird. It's actually an x equals equation. So we're going to be looking at situations where we have x's as functions of y and y's as functions of x's, both directions. So we're going to start getting these weird horizontal parabolas. We're going to get even more weird stuff later. Why? Because it shouldn't be a surprise that are we only going to be dealing with polynomial terms? Of course not. There's trig. Ovals! No! Not an ellipse! It's okay. There are eggs. We'll talk about that in the example. All right. So, yeah, I apologize for the first 2 pages worth of copying. The printer decided it was going to like print those pages miserably. And then if you get to the next page where the notes happen, it's this beautiful, pristine, has all of the grid lines, so I just smile. Okay, so real fast, the pre-cal side. This is not something they will necessarily, they're not going to ask you questions on this, but they are skills that can turn out to be fairly useful. So I want to make sure we at least are comfortable with these. Okay? So looking at my a function, I've got x is equal to the square root of t minus 1, and I've got y is equal to t plus 2. My job is to come up with a parametric table relating the t to both x and y. Now, we do have to be careful with this. T could theoretically be any domain, but in this particular question, T has a natural restriction on it. What can T be? Actually, it's not just positives. T can be all numbers greater than or equal to 1. Because if T is 0 or anything from 1, anything below 1, then what do we get here? A negative value. So we've got to be careful with that. So the T value should start at 1. If my T is 1, what would my X be? What would my Y be? Well, that was hard. What if my T was 2? What is my X? 1. What is my Y? Oh, man. Okay, now here comes the next one. T is equal to 3. Do I really want to do T is equal to 3? Because it would be the square root of 2. And I don't know about you, but I don't really want to have to graph the point square root of 2. So let's omit the T is equal to 3, which would be the next T we would want to use then. The 5. Why? Because it comes to square root of 4, which is 2, and the Y would become... And let's do one more. What would be the next T? I can see you've already figured out the system. And I'll just put dots, and I'll put dots, and I'll put dots. There are more points. There's no limits to the T, so we've got no limits restricting our particular graph. So now we go and graph the points. I'm going to graph the ordered pairs that have resulted from these individual T values. So I'm going to graph the ordered pair 0, 3, 1, 4, 2, 5, 6, 7. Then I realize I'm going to have to keep going. So I wind up getting something that looks like that. Now again, remember, we want to show which direction we're going. So what I do is in between each set of points, I put an arrow pointing that I want to go essentially from point A to point B, giving someone direction to my curve. Ladies and gentlemen, you've graphed a parametric equation. See? Now, what about eliminating the parameter? Sure. If I look at these, the easier function might be y is equal. This is going to take 2 steps to solve. And remember, we're math people. We're inherently lazy. I want to pick the one that's going to be the easiest. And I don't know about you, but I really like this t plus 2 because that means that t has to be y minus 2, right? That was nice. I like that. So if I were to take this and substitute it in right here, this would be x is equal to the square root of y minus 2 minus 1, or we can say x is y minus 3. Is there a restriction on the independent variable here as this is written? Y cannot, y could equal 3. So y must be greater than or equal to 3. And you would have to put that restriction into your problem. You'd have to make that statement, y is greater than or equal to 3, because we want to make sure we have real values come out. Now, an interesting thing, this eliminated parameter does not have one solution. There are two equations that I could use for this. I could make this in terms of y. I could say that y is equal to x squared plus 3, but now when I do my restriction, what's my restriction going to be? Ooh, now this. Now, this is weird. Why does x have to be greater than or equal to 0? Because x squared plus 3, there are no domain restrictions on that. But can you come up with any numbers that would allow me to get a negative x here? So we have to account for the fact that there are no t values that can create negative x's, so there is a natural restriction on this on the x parameter that limits the x parameter to 0 and greater. So if you look at the t, there is no t value that can create a negative x. So since this function, this curve, this planar curve was created utilizing a parametric function where the x cannot be negative, can my function with the removed, remember I'm not representing y equals x squared plus 3, I'm representing y equals x squared plus 3 as a function of these two parameters. Make more sense? It's weird stuff. Bingo. Ha! Good stuff. I love it. All right. Sorry, I get really excited once the x variable and the y variable start moving on their own. It's really cool. All right. So what's up next? We got b. We've got, ooh, this is nice, t squared minus 3 and 2t. There's no restrictions on what the t's could be except that I put a limit on them. I look at the functions, I'll notice that the t variable doesn't really have anything that causes any nasty answers. So since I'm going from -2 to 3, I am going to go ahead and I am going to represent all t variables, all whole number t variables from -2 to 3. What are the x's going to be for this? We're going to get 1, -2, -3, -2, 1, and 6. That's cool. What about the y? That was kind of creepy. All right, so we start graphing the points. We got the point 1, -4. We got the point -2, -2, -3, 0, 2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 1, 2, 3, 4. Oops, just graphed it wrong. What? And you get this lovely looking shape right here. I don't know about you, but it kind of looks like a parabola that's opening to the right. Notice I did not put an arrow at either of the ends. I don't want this to be something that goes on forever, although I do need to put arrows in between the values showing what direction that curve moves in. It's not necessary to draw that arrow in between each point, so don't feel like, but you do need to show a couple of arrows just, that's why I like to do it in between all of them. I can see it, like the lacing on the baseball. Mm-hmm. Okay, So now we have to remove the parameter. What do you want to do? Which one looks like the easier parameter? Y equals 2t again looks like, and there's actually going to be another reason why we like y equals 2t in just a minute. So y over 2 is my t variable. So this becomes x is equal to 1/4 y squared minus 3. You didn't have to square that y, but I went ahead and did it anyways. Is there a limit to the restriction here? There is a restriction on this y. Because look at your function. Your function, if these are the t's that I'm limited to, I can only go from this point to that point. That's a good question. Actually, we actually cannot do this problem with an x restriction. And that sounds really weird, and it's kind of like, why can't we do x with a restriction? The reason why we have to do this y restriction is that, hold on, x has no usable restriction. And I'm going to say due to, and this is going to sound, because I don't know what to actually call it. And I'm going to call it empty space. And what I'm specifically talking about is that space right there. Now, if I were looking at this problem, I may be tempted to say that the x restriction would be from -3 to 6. But then that would be all y's that would result from my x values from -3 to 6. Right? Well, what if I say x equals 6, could I just as easily have gotten this point down here at t is equal to -3? At t equals -3, now I realize that this is limited, but if I only want to go from -2 to 3, but I tell you all x's from here to the 6, I've included t's that I can't use. So in this problem, the x cannot be a restriction, only the y. Again, that's a weird thing to get used to. By the way, that also turns out to be something we have to take into account when we solve this. You all happen to luckily choose this one, but if there's a parabola that I curve back around on, as you can see here, I want to restrict in such a way that the y variable or the x variable doesn't repeat. That was fun. Let's make it even more fun. Trig! All right, so just like every other problem, I need a t, I need an x, I need a y, and we need to come up with a good t to start with. I like that one. It's a great t. Because 3 plus the cosine of 2 plus 2 cosine of 0 is really what? It's 5. And 1 plus 3 sine of 0 is really? -1. Sorry, I said 1. It should be -1. What's the next t you want to use? Pi 6 would give us a value. Pi 4s would give us a value. Pi halves would all, or pi thirds would give us a value. But the problem with each one of those is we'd have root 2s in there, wouldn't we? Yes. Or even root 3s. If we use pi halves, that would get rid of, we're going to get 0s and 1s and -1s. Those are my only option, right? Yeah. Remember, our goal is to try to keep this easy. We're math people. We're inherently, I just need to have something that lets me know kind of what's going on. Does it have to be a perfect graph? No, so let's make sure to keep this simple. I'm going to use pi halves. Anybody like to guess what my next point is going to be? Pi. Anybody want to guess the next one? What? And the last one? 7 pi over 3.5. All right. So at t is equal to pi halves, what is x? 3 cosine of pi. 3 cosine. 3 plus 2 cosine of pi halves. That's hard to say. 3. Thank goodness. What about -1 plus 3 sine of pi halves? Okay. At pi? Three halves. And then you start catching the pattern. All right, let's plot these values. And because this is sine and cosine, we know this should be some sort of curve. And we get this beautiful shape that's moving in a counterclockwise direction. That's right, whatever's in the middle is coming out of the board. All my AP physics people. When you did torque, yeah. 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 Okay. Now, an interesting thing is there's no other. Could the t go into the negatives? Sure. Could the t go into even further than 2 pi? Absolutely. But what's interesting is if I were to take this to the 2 pi plus pi halves, is it 5 pi halves? We'd wind up at the same point. This is going to keep looping around on itself. So we don't have to show any more points. This literally just keeps going around the curve there. So now I have to eliminate a parameter. Now here's the problem that I have with that. I really don't want to wind up with something stupid like the cosine of the arc sine of something. Okay. I also I can't just trade out sine and cosine. It would be real nice if I could just get like sine equals some sort of y variable. And if this were sine, I could just substitute that in. Instead of get the t by itself, just change out the sine t for the sine t, right? But this is sine and cosine. So the way around this is to come up with a good relationship between sine and cosine that would make our problem a little bit easier without having a t. So I really would like to be able to turn this into cosine and sine equals something. So what are some relationships that connect cosine and sine together? Tangent might work, but that would be a tangent of t. Would I have gotten rid of the sine and cosine necessarily? That's it. We can use the Pythagorean identity of the cosine squared plus the sine squared equals 1. Because up here I can figure out that the cosine of t is really what? Just get the cosine of t by itself. What would the sine of t be? All right. Substitute. Whoops, not over 2. That's over 4. So all I did is I took and squared this. I left this as x minus 3 and y plus 1. Real fast, you should actually recognize that equation. It's not a circle, but it's what? Isn't that the equation of ellipse? Wait, how does that work? What does this minus 3 and this plus 1 help me find? Isn't that the center? So wait, we're saying the center is what? 3 and negative 1? Oh, snap. These are this would be the radius along the x-axis, right? Now is it 4?
No, it's square root.
Square root. Oh, wait, what?
Whoa. Whoa. Go back.
Wait, what about? It's amazing. It's like it was supposed to happen. What? We just broke math? Or did we just fix math? All right, so that's the basics. This is like the root of what we're going to deal with, because now we get to add some calculus to it.
Like and subscribe if you're enjoying the video so far.
So what do we look at? If I have a smooth curve C, all right, that's defined as x being some f of t and y being some g of t, one of the things we're interested in is being able to find dy dx. There are a lot of times, there are three different derivatives I can come up with for parametric. I can find the rate of change of y with respect to t. It's telling you what the component for just the y variable is. I can find the derivative of x with respect to t. That would be dx dt. That would give us the rate of change of just the x component. But I'm usually not interested, if I'm launching something really fast, I'm not interested in what is the x versus the y. I'm interested in what's happening at the same time. And that's where the dy dx variable comes in. We can still find dy dx even though x and y are separate. Remember what dy represents. If I say dy, you can read that how? Just the change in y, right? So how would I come up with the change in y? I could just look at how is the y changing with respect to t. And how would I do that with the x? I can just look at how the x changes with respect to t. And if you don't think that that will give me dy dx, one of the things we can look at is I could actually rewrite this as dy dt times, if I divide by a fraction, I can multiply dt, and what's going to happen? What do we get? dy dx. So you can see that having that relationship of dy dt to dx dt can give me a dy dx. Don't memorize this. We're going to find this with implicit differentiation. That's coming in just a minute. Okay. So example 1. Given the parametric equations, x is equal to 2 root t, and y is equal to 3t squared minus 2t, our job is to find two things. The first derivative of y with respect to x and the second derivative of y with respect to x. So let's find the first derivative, because you can't find the second derivative until you have the first. Notice that this is not asking for dy dt, this is asking for dy dx. So I need to find the change of y divided by the change of x. So I need to find how on earth is the y changing with respect to its base variable, divided by how on earth is the x changing with respect to its base variable t. Make sense? Okay. What's dy dt? You know what y is. Y is 3t squared minus 2t. It's just going to be 6t minus 2. We're just going to take the derivative. Dy dt here is going to be 6t minus 2. It would be t to the negative 1/2. Okay. Now typically I would leave this here. We've got some more work we're going to do, and this will be much easier to deal with if we simplify it. So this is one of the few times I'm going to tell you to simplify something on a problem. Even if this is a free response, If I know I need to use this, I probably want to make this easier on myself. So what on earth would, if I rewrote this, how could I rewrite this? Okay, we can move the bottom t to the top, call it t to the 1/2 6t minus 2. I'm even going to take it one step further because right now this was bad because I was using a quotient rule. That's like a mortal sin in this class. We don't want to have to do quotient rule if we don't have to, right? So then we said, hey, let's turn it into this, and we've one stepped up. Now we went from quotient rule to product rule, but if I can, do I have to do product rule here? No, because I can actually take this t to the 1/2 and distribute that and call this t to the 6t to the 3/2 minus t to the 1/2 and make my life a whole lot easier on the next step. Oh, I apologize. I just got really excited about having a t. Thank you. The question was, where did the 2 go? For those of you who are watching the video and not currently seeing it live and are wondering why I'm talking. Now, that's the first derivative. You are done with the first derivative. But that's not the only thing this question asked for. The second thing this question asked for was the second derivative of y with respect to x. So let me ask you this. How on earth do you get the second derivative of y with respect to x? You do what? You take the derivative of what? Which derivative? I've got 3 derivatives. I take the derivative of dy dx with respect to, if I do it with respect to t, is that going to give me a second derivative of dy to dx? No. If I want the second derivative of y with respect to x, I need to take the derivative of dy dx with respect to x. Agreed? Now remember, I told you I'm going to show you how to do this without having to memorize the derivative with respect to t of dy dx divided by dx dt. I promise you we're going to get around having to know that equation completely. Let's take a look at this. Take the derivative with respect to x of dy dx, and dy dx is 6t to the 3/2 minus 2t to the 1/2. Agreed? What is the derivative of the first term? dt dx. Where on earth did that come from? I took the derivative of t with respect to the x. Good. What's the derivative of the next term then? Okay. Now, I see they both have dt dx's, and my goal is to turn this into an equation that just has t in it. So I've got some dt dx's. Those are causing me a problem, right? I'm going to pull those out just so that they're all together. So I'm going to rewrite this as 9t to the 1/2 minus t to the negative 1/2 times dt dx. I factored out dt dx. Now remember, I don't want to have a dt dx. I really just want to have t's. Anybody have a clue what dt dx is? Because I sure as heck don't. I have no clue what dt dx is. But what do I know? I know what dx dt is. Is there any way I can manipulate this so that it's not dt dx, but is instead dx dt? What if I do a reciprocal? If I multiply by dt dx, isn't that equal to dividing by its reciprocal? Yeah. So I could do this. And wait, I need to get rid of dx dt, and I know what dx dt is. What was it? If this were a free response, we'd stop. However, I'm going to take it one step further. I'm going to call this 9t minus 1. Yeah, this would be 1/2 minus a negative 1/2. So 1/2 plus 1/2 is 1. Negative 1/2 minus a negative 1/2 would be t to the 0. See, all that implicit differentiation turned out to be useful eventually. Of course, you've probably never thought to manipulate something by taking the reciprocal of the divisor. What? All right. Part 2. Ladies and gentlemen, I would like you to simply find the equation of the tangent line. I'm going to pause the video so that I don't have a stupidly long video that's already ridiculous. I'll let you work a bit. And there's a whole bunch of information that just magically appeared on the video. That's cool. All right. So if you find the points, you can find the points by substituting 3 pi over 4 and 3 pi over 4. dy dx is dy dt over dx dt. Take the derivative, evaluate at 3 pi over 4. And from here, it's really easy. Plug in a bunch of numbers. Okay, so the question was, what happens if I add the 3 root 2 over 2 over? That'd be fine. There is absolutely, if you really if you prefer this, 3 over 4 x plus 2 root 2 plus 3 root 2 over 2, and if that works for you, certainly that, I will definitely not mark anything off for that. In fact, I think most of the other calculus teachers wind up jumping straight to that point. My brain, I think a lot of it comes from having taught Algebra 1 for as long as I did. When I do point slope form, I do it in its most natural form to not scare students. So the expectation is going to be, in just a couple minutes the bell will ring. I am not going to do the very next question. That will be saved for Tuesday. Your assignment is actually going to be doing the graphing from this and taking a look at the logistic curve stuff. The end of the last packet, there's a bunch of logistic curve stuff, so take a look at those. All right? All right, awesome. Have a great day.